Steinthor. Did I get it? Okay. Thank you. Apologies if I mispronounced your name. Going to tell us about surviving in an age of pervasive DDoS.
Okay, that's it. Forward, back, very simple. Okay, thanks. So, welcome everyone. This presentation is interesting in the way that I'll be talking about a security threat which didn't happen. And why am I talking about this? It's because someone took the effort of building an attack tool designed to launch devastating IoT DDoS attacks, and they didn't activate it. It went out on the internet, it got visible, it got updated rapidly during 1 week, and then they pulled the plug. So the purpose of this presentation is to explain to you what this is all about and how this can potentially impact you and your customers. Because, as you know, when someone has invented the wheel, you cannot uninvent it. So the bad guys have actually taken the effort to do something which we believe to be really scary. Okay. So this all begins with IoT. IoT is basically, everyone today is coming out with a new gadget and connecting it to the internet. For some reason, people believe it's actually really good to be able to connect to your refrigerator, to have your oven go off automatically, configure it, just using an app on your phone to control almost everything in existence. And this is because we like gadgets. We like to be able to play with stuff. And the idea is, of course, some of this will actually have true benefits, like reducing the cost of equipment, in offering new kinds of services, and so on and so on. So all kinds of new interesting things. The problem is, of course, for this business model to work, these things have to be easy to deploy. It have to be easy to use. They have to require total minimal configuration and low cost. Like, for example, the smart bulb, the one which you connect to your house. Not many people are willing to go in and start configuring, setting in the usernames and passwords and setting in access lists and so on. It just has to work. You plug it in and it works. But this, of course, means that everything related to security just went out of the window. Hard-coded username and passwords, all kinds of services, and management things which are enabled by default, and so on and so on. And the reason for this is cost. These guys, they buy the cheapest OSs possible in as big numbers as possible, and they do not want to play with it. They do not want to make life difficult for the customers, which means these things have bugs, and they cannot be configured, and they will just cause problems. So, actually, one very good example, which I saw earlier, regarding the light bulbs. This is the intelligent light bulbs, which you see up here. Some guys in Israel actually came up with a really cool way to use those light bulbs to inject malware into air-gapped systems which are supposed to be totally not connected to the rest of the world. So they could actually fly, what they did was to fly a drone outside the building and send a signal, and were actually able to control the light bulbs themselves, just by using lasers connected to the drone. They actually were able to attack the light bulbs, and then what they could do is actually to control the light bulbs to send signals to scanners. Because what is a scanner? Scanner uses reflected light to read in information, and you can actually control these light bulbs down to send a pulse of light down to 25 milliseconds, because no one can see. So they use those to actually, if you have a light bulb, IoT light bulb in a room with a scanner, then you can actually send extra signals to the scanner itself, inject malware to it, and then control it. Which means you can then go off and steal data. And how can you actually get the data out? Well, there's Morse code. Have those light bulbs, which you already control, send out the information out the window in the other direction. Slow, but it actually works. So, and the problem is, of course, these things light bulbs and the cars and the UHD TV, it's just a PC with a specialized interface. It's a computer running as cheap software as possible, which will never be upgraded, never be passed, and there's no, even if you want to change those things, you cannot do it. And we go off and buy them. So, what does this actually mean? We got things like these. Last year, we saw DDoS attacks which are bigger than anything we've seen in existence. And the reason for that is, of course, all those webcams and DVRs and all those things which people, for some interesting reason, decided to connect directly to the internet. Well, if you have a webcam, which is in your living room or something, then most people would try to have it behind a firewall or something, but some people, well, it's too complex, so I just give it the public IP, because that means I can connect to it from wherever I am. But if that device has a username password, which has never been changed, then the bad guys actually figured out that you can actually connect to those things and inject new software. There have been discussions about how the volume of those things, how many devices were out there which were vulnerable. But one number which has been thrown around is about, when this was about 1.5 million IoT devices were being controlled at one point of time last year. And those things, they were used to attack the Olympics, they were used to attack DIN, they were used to attack Krebs, and so on and so on. And again, the attack volumes went up to 1 terabit or beyond, and caused a lot of interesting problems, with devastating consequences. This is actually a very interesting one. So let's go a little bit more into details about what this actually is. So the thing is, there are a lot of people out there which earn their money daily by creating malware. That is, they're professional people which have a lot of understanding about protocols and really understand the network, the internet, and they are out there building tools to attack other stuff. It could be, that is, people which are actually employed by a government. In many cases, it's people which are working on their own, and then they sell their software to the highest bidder. So Mirai is one of those, and this was used to run some network attacks. And the interesting thing is that the source code was actually published in August 2016, meaning anyone can download it, play with it, change it, modify it, and so on. And the Mirai code actually contained a lot of different DDoS attacks which have been used in the last year. So basically bundling them all together in one easy to use and deploy package. So Mirai works in the following way. It basically, when a device is infected, it begins to scan. It tries to find other devices to infect. And Mirai, in this specific case, scans on TCP ports 23, 23, and so on, as you can see up here, basically trying to connect to a device using Telnet, and then it has a list of hard-coded usernames and passwords. Of course, admin, no password, admin, admin, and so on and so on. And then if it's successful to log onto that device, then it actually will then tell the command and control server, here's a new target. The command and control server will then inject malware to it, which then will take control of that device. And then that device will then start scanning and doing bad things. Most of the devices which were used last year came from 3 manufacturers in China, because that's where they create almost all those cheap devices. The interesting thing is, one of those things were actually patched back in 2014, but only for the English version of the software. The Asian ones, or the Spanish-speaking, and so on, they were not patched. I'm not sure exactly why that happened, but it meant that a lot of the attacks we were seeing, the majority was actually coming from non-English-speaking part of the world, due to this. So the attacks which Mirai offers are the typical one, like UDP flooding, TCP ACK flooding, TCP stop attack, which they call it, which basically means the device establishes a three-way TCP handshake to someone and then starts to send some kind of junk through that connection. And then you have the usual GRE packet flooding, HTTP flooding, and so on. And one of those, which was actually used to tremendous effectiveness last year, was the one at the bottom, the DNS water torture, basically creating random DNS queries and then flooding them towards a DNS server. The initial version could not send spoofed attacks, but this changed back in 2016. And the reason why this is interesting is that as soon as you're able to spoof a packet, that means you can actually start to use it to send reflection attacks. That is like send a DNS query, a small query to a DNS server, asking for all the records in a zone and have that sent to the target, which gives you an amplification factor of up to 160. So instead of sending one packet, or if you send 1,000 packets, that gives you a certain amount of bandwidth. But now you can send those same 1,000 packets to someone else, which will multiply the number of bytes by 160, which is a lot more effective. So basically, they dramatically increased the attack capacity of this code. Here's an interesting picture. When we started to look at this, then what we did is we deployed a number of VMs which simulated an IoT device in different locations in the world, gave them a public IP, and then we just sat down and monitored what was going on. So during 2 weeks' time, back in 2016, then we got to about 1 million login attempts from about 100,000 unique IPs. So basically, as soon as you put a device out there, someone tried to attack it, log onto it. And in some regions, this meant that we had more than 1 attempt per minute. So basically it means, if you go off, buy a webcam or a device which is not secure enough, and you connect it to the internet, within 1 minute, someone else will own it and control it. And this is actually a lot worse than back in the old days when we had Windows XP. Then we had 3 minutes before someone took control of your XP box and owned it. IoT device, 1 minute. And this is still happening. These guys are still scanning and trying to attack devices. So the situation today is like the iceberg. The unprotected devices on the internet, and the estimation is that about 5% of the total population of IoT devices are out there. They will get infected within 1 minute. But the IoT devices which are behind firewalls or some kind of a NAT device which makes it impossible for someone to actually reach those and infect those is about 95%. And until January 2017, we thought this was good. If you have a vulnerable device, you just put it behind the firewall, don't put it on the internet, and you'll be okay. But this changed. The reason for why this changed is that these guys, they came up with a piece of software which actually no one had seen before, was crossing the multi-platform gap. Basically, it means they created a piece of software which infects Windows computers. Just uses different techniques, I'll come back to that later on. It infects those Windows computers, but as soon as that computer is infected, it begins to scan for IoT devices around it. Both Windows and IoT. If it finds a Windows computer, it tries to infect it. If it finds an IoT device, it actually then kicks off the IoT infection code, which connects to the device, tries to find out what kind of platform it is, and then it has all the different malware bundles, that is for different platforms as part of the payload, and then injects the appropriate one onto the device and infects it. So we have a Trojan which is both capable of infecting Windows, but also capable of infecting a lot of other type of devices running different code base, different platforms. And this is actually built in a way which is modular, easily upgraded, and can do a lot of really bad things. So the thing is, this is actually based on code which was originally seen back in 2016. So someone took existing code base and added the IoT infection code to it. Then people have been guessing, who created this? Why did they create this? And so on and so on. Some indications say it's built in China, but of course, if you want to hide your tracks, then you put something in your code which points towards China or North Korea. It's easy. Blame someone else. Could be anyone. We really don't know at this point of time. But the interesting thing is, this was launched back in February, which means we saw the malware coming, it began to infect computers, and during a 5-day period, I think, if I remember correctly, there were 3 different versions. So actually, based on the feedback, based on what was happening, the bad guys came up with new versions, with new capabilities, which made it possible to infect even more, the greater amount of computers and so on and so on. But on day 5, this was shut off. Basically, the command and control servers and all the infrastructure taking care of the distribution just disappeared. Why? Well, no one really knows. Was this an experiment? Had someone coded this and wanted just to do a small test to see if it worked? Was the test successful or not? We don't really know. But someone created this. You can go out and download the binaries. They are available everywhere, and it's really easy to do the reversing, basically, to understand how it's built. Like I said, someone created this technology, and this is the first time we have this multi-platform code base. Some people say, hey, is this the same as Stuxnet was doing? But Stuxnet actually infected the computer and then sent malicious commands to devices directly connected to that one. It was not trying to infect the industrial controllers, it was actually telling them to do bad things. But this actually hops to different platforms and infects those. So, as I was explaining, this goes off and subverts all those innocent IoT devices into zombies. Basically, when it's inside your corporation, it begins to do bad things and subverts them into those evil devices, which will then try to reach out, talk to the command and control server, and do bad things. So, you're probably wondering, why am I telling all of these things? Well, it's interesting in a way, but what does it really mean for the internet and enterprises? I'll come back to that a little bit later on. Because here's one thing. Ransomware. We all heard about ransomware, the software which goes to your computer, it locks it down, it encrypts everything, and you have to pay some bitcoins to get your data back. The thing is, what we also saw in 2016 is that the ransomware code actually began to include DDoS code to launch DDoS attacks. We also saw that code which has traditionally been used to launch DDoS attacks was also containing code for ransomware. And this means, because if I can infect your computer, then, and it has data which is important for you, you'll hopefully pay me some money. If I could then use that same computer to actually launch attacks against a service which you depend on, that's a lot more effective ransomware. It actually will cause a lot more damage, but the idea is basically the same. I want to cause damage, I want to make it impossible for you to access your data or your services, pay me money, and then I'll stop. That's the idea, basically. So we actually saw those 2 areas, ransomware and DDoS, starting to merge. So, what does this actually mean? First of all, this means that if you have a single infected computer, which you then take back home, you take it and plug it into your network, that is the network where you have all those fancy firewalls in front, protecting from the bad guys, this will now be behind the barriers and is now able to connect to your IoT devices and infect those. And that means those devices will now start, of course, to infect other devices. They could be used to do the traditional thing, launch outbound attacks against someone else, or, if the guys are clever, launch attacks against internal resources or try to use them as a part of a multi-phase DDoS attack. So, the question is then, how well prepared are the SMBs and enterprises in meeting this threat? Because this is a tool focused on enterprises or internal networks. Of course, you have your own internal networks at home and so on, but this is mostly focused on those on the enterprises and the SMBs. And the thing is, in this specific case, then actually SMBs are probably better at IoT security than enterprises. And the reason for that is that in large enterprises, the guys taking care of IoT, that is the building systems, the elevator systems, the air conditioning, and so on, they are not part of IT. They take care of their things, but the IT guys and the security guys, they take care of what's related to the network. But in many cases, those things are actually running on the same underlying network. In SMBs, then usually it's a lot smaller. That means the guys buying those webcams or whatever, they are usually the IT guys, and hopefully they have some kind of clue and actually try to secure them, hopefully. But then you come to the question, how many people actually upgrade the software on those devices? How many people actually take care of isolating these things, have the IoT devices in a separate network, having some kind of control of traffic going from the IoT devices to the rest of the network, and from the rest of the network to the IoT devices, and so on and so on. And based on my experience, before I joined Arbor, I worked for Cisco, and the answer is not many. There are not many organizations which actually do this properly, because the bad guys are out on the internet and the good guys are on the inside, right? Yeah. So, but actually when I began to think about this thing, then I thought, I actually bought some webcams back in 2010. I connected to my home network, and did I actually do the right thing? Luckily, I did. I was really proud of myself, because I actually thought it would make sense to have them in a separate VLAN and having a firewall, okay, just a small ASA or whatever, control the flow of traffic from the IoT devices, all the webcams, to my NAS, which is actually looking at the recordings. And in this case, I'm not able to reach those directly. I cannot cause bad things. And those IoT devices are not able to reach the rest of my stuff. So I was happy. If you're going to ask me, have I upgraded the software on those webcams since 2010? Okay, next question. Okay. So let's take a look at a typical enterprise network and a typical network design. Looks interesting, lot of boxes, really expensive, but usually it's set up like this. We have the bad guys out there on the right-hand side. Then you have some security boxes. They take care of our security of the firewalls and the IPSs and the IDS, and so on and so on, just in a or in a rack somewhere and taking care of stuff. And then you have someone inside. You guys, when you come back from NANOG, connect to your network, plug in, and that means you're sitting there in your branch office and life is good. Except at NANOG, someone actually had this virus and was busy infecting all the laptops in this room. So when you come in there, what happens? You plug it in an internal network. Could be wired, could be wireless, could be VPN, doesn't really matter, because your computer will start to scan. Local subnet, then potentially other subnets, RFC 1918 or whatever, and continue. So basically, what are the potential targets in this picture? Well, these are the webcams. Everyone has a webcam in your data center, of course. You want to keep track of who's in there. By the way, have you upgraded the software on your webcams recently? Don't have to, they're secure, right? So in this case, we have all these webcams all over the place. So what happens is that this guy, he plugs in his laptop, and it begins to scan. So it just probes the internal network, and it finds a webcam, which is then infects. Then it continues, tries some other subnet, no success, continues, go to the next subnet, and so on, and so on, and so on. But at some point in time, you see this black arrow popping up. In this case, the infected device will actually start to do its own scanning and try to find other targets, because that's how the code is built up. Which means, after a while, you will, if the attacker didn't do things properly, you will actually have tons of ARP requests, tons of small packets, TCP SYNs, and all those things going back and forth in your network. And in some cases, this will be sufficient to actually crush devices. I'm not going to name any names, but there was a certain service provider in Europe which had issues with exactly this problem, because infected CPE devices, they scanned so aggressively that the DSLAMs went down, causing an outage of 1 million users or more. Afterwards, the attacker, he actually sent an email to the organization and said, sorry, I didn't mean to do this, but, well, but the guy was stupid and they apprehended him and he's in prison, so that's good. But just this scanning itself can cause problems. Because the thing is, behind the firewalls on internal networks, you have all those devices which are stateful, meaning they keep state of sessions. They reserve memory for what's happening. They know there's a SYN, I need to inspect it, and so on. You have load balancers, ITSs, firewalls, name it. And in many cases, those things will collapse. And you have those ARP tables, which can also fill up. Lots of things which can go really wrong when you have these huge volumes of scanning traffic. So let's assume that this guy, someone is controlling these devices, and now suddenly he has gained control of, well, 100 new webcams somewhere. He doesn't really care, but now he's going to attack someone. So he tells all those devices to, well, go off and launch your attacks. Could be TCP SYNs, could be UDP flooding, could be basically whatever. He just tells them, send packets as quickly as possible through your network. And what will happen? Well, what will most probably happen is that the internal network will totally collapse. Because enterprise networks are not designed to pass packets through without doing some kind of inspection. So looking at this in more details, because they will launch all those bad things. And these devices, which you have, the routers and switches and so on, they will, most cases, when this flood of packets go through, they just basically collapse, and the internal network dies. Someone mentioned to me recently that actually this could be one of the reasons why the guys who created this malware tool, when they began to look into this in more details, they say, what's the point of infecting all those webcams into enterprises? Because as soon as I turn them on, they will kill themselves. Because yes, this could generate tons of traffic, but if the internal network dies, then basically it will not forward anything, and that means those devices will not be effective anymore. Maybe. But coming back to what I said earlier, is if the guy is clever, and we talk about things like ransomware, but meaning if he really understands how the effect of this on internal networks, then maybe instead of just launching outbound attacks, let's launch internal attacks. So here, instead of just blindly sending attack packets in all directions, then maybe he does some kind of reconnaissance. And a webcam in a data center somewhere where you have not taken care of the segmentation will probably be able to pick up things like SNMP packets going past, looking at who's controlling it, looking at IP addresses, sending an outbound packet, being able to, finding out where it is actually located. In this case, it's located at my target, whatever that target is. So what are the bad things an internal device can do if there's no security in place? It can do things like sending out routing updates. And what would be the most effective thing to do? Well, let's black hole the NOC and the SOC. Stop the guys operating the network from being able to actually do anything. Attack the DDoS mitigation services, because at the same time as I'm doing this, I'll be launching a big attack from the outside. So in this case, then basically the guys defending the network would then not be able to actually enable the defenses to stop the attack from the internet. So if I do this in combination, yeah, it can be really interesting. So he would, the clever guy, and again, the code which we identified back in February was not doing those things. But the thing is, it was actually designed to download additional modules. When it, let me explain a little bit more. So when the malware kicked off on those Windows PCs and on the Mirai devices, then it actually contained code to download extra modules which could basically do whatever. So it was really easy to extend with new kinds of code. We never saw that code because the control and service went down. We don't know exactly what was doing extra things, but it had the code ready to do it, to upgrade itself and install new modules. So in theory, where they're doing this, we don't know, but very easy to do. So they could do things, like I said, do the reconnaissance, attack the IGP, take on the network, launch internal attacks, launch attacks combined with external attacks coming towards that organization. And as I said previously, this would probably make the internal network collapse. And after about 15 minutes, you have a timer in there, you stop things, and then you send the email saying, hey, please pay me some bitcoins or I'll continue. And the thing is, if you haven't protected your network correctly, built it in a segmented way, it is really too difficult to do it well under attack. There's actually basically no way to do it properly. So, and then of course the question is, can a small device like a webcam or a light bulb or those things, can it actually cause all those problems? Most of you already know this, but I'll include it just in case. Because every network device, router or switch, it has its fast path and its slow path. And those devices are designed to pass traffic, transit, and this will happen in hardware, we'll have no problems, things are good. But received packets, which is destined for that specific device, like routing protocol updates, or any other kind of traffic which controls the behavior of that device, has to be sent to the main CPU for processing. Can you protect that? Yes. Is it protected by default? No. Someone has to take the effort to do this properly. You guys do it on your on most of your routers and switches who are on the internet, because you know things will go really bad if you don't do it. Enterprises traditionally do not do it because they are in a safe area, I think. So, but most devices are capable of protecting themselves, but this is not enabled by default. So, received packets, then of course you have the exception packets, TTL expiry, IP options, and other bad things that basically mean that the packets have to go past from the data plane up to the CPU because something has to be done. Again, can you protect against this? Yes. Do people do it? No, and so on. And then, of course, non-IP packets. Like, if you don't send an IP packet, you send ISIS or something, it will, in almost all cases, have to go to the main CPU, just to have more fun. And of course, if the attacker is clever, and even the tiniest thing with a CPU and an IP stack will, in most cases, be able to send enough packets to cause problems for almost every network device if it is not secured. This is an old test. I actually did this back in probably 2010 or something. I was attacking a Catalyst 6500, a Cisco Cat6K. And 300 packets per second against the Cat6K, which was not secured, was enough to take it down. Basically, it was as simple as sending TCP SYN packets against the BGP protocol. Nothing more. Because then the BGP protocol was busy processing all those SYNs, which means it could not have the power, enough processing left to send hellos or receive hellos, or basically the BGP adjacencies went down, that means the routing went down, things got bad, and so on and so on. Yes, again, if you protect that device, nothing will happen. So, how can we defend against those things? Or actually, in this case, what should you be telling your customers if they get hit by something like this? If the bad guys decide to actually relaunch this attack tool, or if someone else actually has picked up this idea and tries to do some bad things. So, I like castles. I think what people did back in the old days with castles and walls and all those things is truly fascinating. Of course, technology today makes it totally irrelevant, but back in the old days, a well-designed castle was actually a pretty difficult thing to attack, because they focused on things like layered defense. They focused on different ways to detect attacks. If you're trying to dig under a castle wall, they had people actually listening to this, or it had those moats. Basically, you dug a tunnel, and then suddenly, because there's a moat, then you got all the water into the tunnel, and nothing happened. And basically, everyone drowned. And so on and so on. And actually, the way most castles were taken over back in the old days was bribery. Give someone enough money, and he'll open the gates, and, well, then that's it. But let's look at this castle here. The reason why I'm going down this, I think it's interesting. It has some relation to what we will be discussing a little bit later on, and it's also a little bit fun. So in this case, this castle is in Slovakia. And let's assume that the things you want to attack are actually in that tower in the middle. So how would you attack that castle? And no, you're not allowed to use dragons or anything like that from Game of Thrones. So let's assume you want to get access to this. You know that they have, let's say, 1,000 guys defending. You have about 4,000, but you have to be rather quick because they will scream for help and they will get reinforcements within a few days. So you can't just do a normal siege or something. So where would you attack? Probably not on the left-hand side, because you cannot climb up those things. Which means you will probably have to go on the right-hand side because the walls are lower. It's easier to access. But if you take a look at an aerial view, and this is how you traditionally design those things, it's a layered defense. The outermost wall, the ones which attackers will begin by attacking, is actually just an area which is easy to, you will defend the long wall. If you have problems, then you just retreat to the next wall, and hopefully slowing them down. Because it's all about slowing the attacker, because in security, there's no 100% security. It's about slowing them down, making life so difficult that you can actually get reinforcements or make sure that the attack is not successful. So that's what they did. Outermost wall. You get into this big area at the bottom. And then you have to go, then there's another wall. It's shorter, which means, okay, you've lost some defenders, but now they're more effective because they have a shorter area to defend. So let's assume they get across wall number 2. Well, there's another wall, even better defended, and so on. So you continue and continue. This all takes time, and the reinforcements are hopefully getting closer and closer by every day, or every hour. So one interesting thing is, let's assume you managed to get into one of those towers. And here's another thing which I thought was really interesting. This is a typical castle tower, and the stairway was actually built clockwise. This is a design feature. It's a way to take advantage of your environment, your organization, the way you design the network to give you the advantage if something is really going wrong. But there's an exception. If you're Scottish and your family name is the Kerr family, they did things the other way around. And why did they build the stairways in a counterclockwise way? Because they were predominantly left-handed. And they thought they were really good fighters, so they built the stairways the other way around because that will give them the advantage. But there's a slight problem with that. You're actually making it a lot easier for almost everyone else, which is right-handed, to hit you. Okay, pluses and minuses. Okay. So let's go to what's interesting. So it is not easy to defend against those things, because enterprises are traditionally not built in a way to be able to survive in such a way. You guys have been doing this since the start of the internet. You have devices out there which are capable of passing malicious traffic and good traffic without collapsing, in most cases. Yes, if there's really big attack, then maybe you have problems, but you know how to protect your devices, you know how to design your routing protocols, and everything to make sure that if things go really bad, you are able to keep your network up and running. And this is actually a way for the attackers to, if the internal network for the enterprises is strong enough, let's use that word, then that means enterprises will now be able to start to launch really effective DDoS attacks going from outside. That's for inside to the outside. So, what does this mean? What I'm trying to say is that we should all try to educate people about basic, what I would say, security 101. How to build networks in a secure way. Yes, it's costly. People, and as I explained previously, if something costs money, then we'll probably not do it. But they have to do something. And even the smallest change in security posture will actually help a lot in this. And you all know this. This is how you fight DDoS attacks. You do your preparation. You harden your network. You have detection and identification in place. You can see what's happening. You classify what's happening. In this case, classify then to traceback. And in this case, traceback is really important because it will tell you if the attack is coming from the outside or coming from the inside. And then you react in the best way, and then you do post-mortem, find out what went right, and then you make the necessary changes, and then continue. This is how you fight attacks. These are just some of the things which people should be doing. That is basically coming back to the BCPs. This network segmentation, which I talked about. That's extremely important. Take any things you don't trust, put them in a separate VLAN, filter the hell out of them with a stateless device, not stateful, stateless. A router with ACLs is really effective. And you'll hopefully be a little bit better off. Then, of course, routing protocol security, having some way to mitigate DDoS attacks, flow telemetry, understand what's happening on your network, be able to detect what's going on, be able to classify what's happening, and then trace back to where it's coming from. Scanning for internal services, like an IoT, a single infected web camera, which can attack a DNS server on the inside and do reflection type attacks, basically amplify its attack, can be really effective. How easy is it? You could solve that very easily with just one configuration line, but you have to do it. Then, of course, the usual anti-spoofing, stop packets, and so on and so on. The thing is, you guys know how to do this. And if a customer of yours would get hit by something similar to this, they will start screaming and maybe if you're offering some kind of security service to them, they will start screaming at you guys and saying, why are you not stopping this DDoS attack against me? I'm being DDoSed to death. Please help. But you can't, because this is happening on the inside of the network. And most service providers, when they offer DDoS services, they're protecting the connection towards that specific customer. So if you want to be able to help them, and actually in this case, sell them additional security services, then help them to see what's happening. Take some net flow data from them, so you can see what's going on. Have a way to help them to mitigate those attacks. Help them to become more secure, because you know how to do this. They don't. They will be screaming for help, and you can make money. That sounds like a nice deal, right? So, and like I said, if everyone would take care of doing things properly, then this is not a problem. And that's the good thing about when you see a new type of attack like this. These guys, someone developed the attack technology to be able to do those things. Me informing you and you informing your customers means that maybe this attack type will never be used. But what have we gained? We've gained the networks will be more secure, the customers will be more secure, and hopefully life will be a little bit better in the future. So I think everyone can gain by listening to this and then trying to educate their customers. So basically it means, coming back to our castles, the attackers are inside the castle now. They're no longer just on the other side, they're actually on the inside. And they have now the possibility to infect all those devices which you have been ignoring totally and use them against you. You can't solve this by hardening your network defenses and make sure things are okay, because you cannot do it while during attack. It doesn't work. If you do things before, you will be a lot better off. And so implementing those BCPs, security BCPs, will be a lot beneficial, offers you the possibility to get closer to your customers, be more relevant to them, and be able to help them and make money at the same time. So thank you for listening. Questions? Or is everyone hungry?
Hello, Patrick Gilmore, Markley Group. I'm sorry if you did this in presentation, but I don't recall how you thought a camera could attack an IGP. Do you think enterprises just leave their OSPF open to anybody to send it a packet, or how does that work?
So how could the camera infect an IGP? If the camera is if they haven't separated from the rest of the network and they're actually able to send packets to your router, and that routing protocol is not secured, there are many different ways, of course, to attack it. In fact, inject fake packets and so on. And there have been a number of presentations at Black Hat and DEF CON in the last years which explain exactly how to do this. So if the device is physically on the same segment or be able to send packets on the same subnet, it can do a lot of really bad things and take down the IGPs.
Thanks.
Don Smith, CenturyLink. Do you know why Mariah spread so quickly? Do you know why it spread so quickly? Mariah?
Have you seen this live, the attacks?
Yes.
No, we haven't. The only thing we saw was during those 5 days when they were rolling this out. It's like they built the bomb, put everything in place, but the clock stopped at 1 second for some reason.
I'm sorry, I asked, do you know why it spread so quickly, Mariah?
Do you know why Mirai spread so quickly? Sorry. The reason for that is because there were so many devices out there which are not secured. There were I'm not sure exactly how many, but at least in the millions devices out there which were not, where the password had not been changed. But doing the scanning, and as I said, it takes about 1 minute to get the device infected, then it just got integrated into those botnets very quickly.
Yeah, it used a decoupled SYN scanner, so the SYNs were sprayed as fast as possible, encode the IP and the ISN, and if you reply, then I know who you are. It's called a decoupled SYN scanner. It's a decoupled SYN scanner. You don't wait for the ACK. You don't wait for the ACKs. You send as many SYNs as you can.
Yep.
Put
Correct,
the IP
yes.
in the ISN. Then you get it.
Exactly. Okay. Okay, thank you everyone.
Good job, Mario.